Justin, and I'm from Singapore, currently employed by the National Research Foundation in Singapore. And I'd like to tell you today about a kind of a mode that occurs at the edge or surface of a metal, anomalous Hall metal, which is kind of confined to this edge, right? And so as you can see, this is my electrostatic, sort of my electric potential profile. It's kind of confined to this edge of this metal, this anomalous Hall metal, and it can move in a chiral fashion. So propagation going down this way will go with a different speed of frequency than propagation going down this way. So there's some chirality going on in this system, and I'd like to tell you how this can be achieved at zero magnetic field. And this is due to very curvature type effects. So we'll get into that. So before we get into that, we'll tell you a little bit, a small introduction, chirality, and then we'll get to part two where we introduce these kind of plasmons, which we kind of call very plasmons. So before we kind of like dive into this main meat of this talk, let me just kind of remind you where we've kind of seen chirality before. So we're very kind of familiar with Lorentz force. When apply a magnetic field coming out of the plane, for example, and if I've got a charged particle, I get Lorentz force. And this means that, I get this particle goes around in a circle, called the cyclotron orbit, and it goes around with some kind of frequency, this cyclotron frequency EBU. Okay? And so this is all very well and good. You can say, fine, let's try and see what this gives us. You can apply an electric field, and the cyclotron orbits drift in this plane, and it's drifting transverse to both the electric field applied, as well as the magnetic field coming out of the plane. And so these are called drifting cyclotron orbits. And this gives you the Hall effect, for example. You can measure the Hall effect, depends on the density, and if we kind of push up the magnetic field to quantizing values, we get something very nice and beautiful called the quantum Hall effect, where you get these plateaus of Hall resistance, which go as h over v squared. So this is kind of nice and interesting. But it's very interesting from a physics point of view, but it can also be important from a technological point of view as well. So let me just give you one example. There are many examples of behavior like this where it's important in technology, but let's think about just one simple example from optics. Right? So there's something called an isolator, and this what happens is forward propagation is allowed through this little box here, but backward propagation is disallowed. So that means if I push light beam going through this special box here, I'm allowed to go this way, but I'm not allowed to go the other way, right? And this is called an isolator. And the reason why this is kind of important is because I have, for example, a laser. So in a laser, this cavity is highly nonlinear. I want to get light out of this system, but I don't want, stray light to come into the system, because if stray light comes into the system, it messes things up, it's highly nonlinear, and I don't like that. And so that's why isolation is very important, and people, think about how to build these isolators using various methods. One very simple method of doing it is via, just using magnetic field, I just told you. So they apply magnetic field in this special thing called a Faraday crystal, and on either side of this Faraday crystal, they put these cross-polarized things. So these are rotated at 45 degrees. And so if I apply magnetic field going in a direction here, the polarization of my light will kind of rotate a little bit, and it will allow for forward propagation. So it passes. So this tick goes right through. However, because magnetic field picks a chirality, rotates it in the other direction, it rotates it in a particular direction. And so if I come in the backward propagation direction, it blocks it. And so this is kind of useful this is one way of achieving isolation in these optic systems. And one can say, okay, fine, this is very well and good, but I don't really like to apply magnetic field on chip, maybe. So if I want to make, say, an isolator on chip, if to apply a magnetic field, it's, for very clunky. Maybe I don't want to do that. So a question one might ask is, can I do this but without magnetic field? Can I try and do all this kind of nice stuff, without magnetic field? And we can see if we can, instead of using magnetic field, an externally applied magnetic field, can we maybe do and achieve chirality without magnetic field and maybe use crystal field instead? And so one thing to look at is Berry curvature. And as we had kind of talked about before, Saturday, some wave packets going through certain special crystals can experience some kind of self-rotation. So this is, I take a wave packet and put it into the crystal, and it just wants to go around in a circle by itself, just around itself, exhibits a self-rotation. And one can describe this as a dual to the Lorentz force in semi-classical equations of motion. So if I'm usually kind of used to just having group velocity, d epsilon gp, where this just gives you the velocity of the material, and energy determines, so the energy dispersion relation determines the velocity of that material. And I'm also kind of used to having a force equation like this as well. It's my electric field and I'm on the Lorentz force, which we just talked about. But there's an additional thing in these crystals where knowing just the energy dispersion relation of my system is not enough. I need to put something extra in, which is the enormous velocity, and I need to understand, and this comes from the Berry curvature of these certain special crystals. And this gives rise to a Hall effect, as one might expect as well. For example, if you just want to see this by applying electric field, just going up in the plane here, and I think of Berry curvature as going out of the board, so it's coming out of the board. What happens is I basically get, if I just use my right hand, I find that there's an extra velocity going in this direction, going to your right. So this gives you a Hall effect as well, and you can say, okay, fine, where can I see this? Well, I can see this in old models. For example, the Haldane model gives me some kind of Berry curvature as well in this material. But I can also see this in experiment, and called atom experiments, whereby they try to redo this, not redo, but they try to experimentally realize the Haldane model here, which is a kind of a hexagonal lattice, but with complex second neighbor hoppings. They try to do this in a cold atom setup, and we're able to actually image the effect of the Berry curvature in this system. You can say, okay, fine, this is very well and good. Can I see this in a solid state system? And you can actually as well. So these magnetically doped topological insulators done by the Chinese group in Beijing, they were able to actually get a Hall conductivity in these systems at B equals to 0. And they'll also be able to achieve the quantum effect of this, whereby it was kind of quantized E squared over H, even though sigma xx, which is this red curve here, was quite small, right? So just trying to show you that materials which have Berry curvature have this kind of chirality at B equals to 0, right? So now we have all the kind of ingredients, background maybe to try and ask the question, what happens when I try to introduce electron interactions in the system? And to do this, this next part I'm going to tell you about new collective modes in this system. And this work was done with Microdna in Copenhagen, and more details can be found in these this posting in this paper here. Very good. Okay. Very good. So if I have a metal, usually or system, I think of when I apply interactions, things can happen. Some very exotic things can happen, but also some very run-of-the-mill things can happen as well. What happens is we can have a plasma, for example. So and these are the collective modes of this foam liquid, this metal. In other systems as well, we can get collective modes as well. And if you're not too familiar with plasmons, I'll just give you the bare bones kind of rundown of what a plasmon is. What it is it's this kind of traveling kind of charge density wave of charge density inside my material, which is this excitation of this metal. These are collective density oscillations of my metal. And so how do I see this? How would I bare bones arrive at a plasma? So I can say, fine, what happens is I take a metal and let's displace it a little bit. Let's apply a little bit of density and homogeneity in the system. Let's say I apply a very weak kind of plane wave density and homogeneity. What happens is this will give rise to some kind of potential profile as well, interact with the jelly system, and this will also give you an electric field. And so we know that the charge density of a metal obeys some kind of continuity equation, right? So we have this kind of simple kind of continuity equation where the amount of current or velocity entering the system is kind of conserved. And we also know that it also obeys a force equation, right? So dt, dp dt, can be forced by an electric field. But if I now kind of displace the density in the system, and I create some excess of density homogeneity going up and down like a plane wave, this actually gives rise to some kind of potential profile that gets created self-consistently as well as system self-generated. And then I would get some electric field, which then drives the momentum. And since I know that momentum is related to velocity by this constitutive relation, velocity is p over m, or momentum is m times velocity, then I know that this will change this kind of current density term here, this v here. And so this is a self-consistent relation that goes back and forth, and I get a plasma. So I get this plasma which propagates into a system. So very good. So now we understand what a plasma is in these metals. What is anomalous? And so why do we care about this? So the reason why we care about this is in recent years there's been this great interest in plasmons, and the reason why, there are many reasons why people are interested in plasmons, but one of the reasons why people are interested in plasmons is because it can confine light to a very, very small volume, smaller than the wavelength of air. So the plasmon wavelength can be much smaller than the wavelength of light, the same frequency in say, vacuum. And as a result, what you can do is you can confine light to a very small mode volume and then hopefully propagate this, manipulate it on chip. And that's a great dream, and there's actually a lot of kind of groups that are kind of pushing this agenda in say graphene, for example. So the reason why graphene could be quite useful for this is you get tunable graphene plasma dispersion. You still get high field confinement, so the electric field is really concentrated, really small mode volumes. And as a result, you can do lots of nonlinear things with it because there's a large electric field as a result. On top of that, the hope is to achieve very long propagation of these materials, so much so that you can allow these plasma polaritrons to kind of propagate for some distances and be able to use it as optical interconnects. So one might say, okay, fine, how does Berry curvature alter these plasmons that we have, these collective excitations in the system here, and maybe this can allow us to achieve some of these this earlier thing of optical isolators that we talked about from before. If I couple light into the system, and then they have some kind of this system, this metal system has plasmons, but they also have Berry curvature. Maybe they can propagate in a chiral fashion. I can manipulate it in such a way that I get some kind of non-reciprocity for non-reciprocal propagation and isolation. So now that we understand this kind of more general idea, motivation of why we're doing this, then we can say, okay, fine. Maybe if I add interactions and Berry curvature to metal, maybe I get something like Berry plasmons, right? And let's see how that would happen. So let's start again with this equation of motion. We have our velocity again. So we have group velocity, we have anomalous velocity inside the system here, and then we say let's displace our system a little bit. Let's apply some kind of density in homogeneity in my system. So I told you again, density from inhomogeneity in my system will create a potential profile, and that potential profile will give you an electric field. Why? Because of this electric field is minus grad phi. So let's do that, and that means that this density now is going to propagate with an extra velocity, not just given by loop velocity, but this extra thing. And so what do I mean? I mean that when I write down the continuity equation, something like this, where I get dn dt, the velocity changes. So it's no longer just p over m, which I'm very used to, which is p over m. I get this extra component as well. And that extra component now depends entirely on this phi profile that is created by this density and homogeneity that I've created. Right? So it gets this extra component, and now it wants to propagate with this extra velocity. You say, okay, where is this velocity pointing? Well, it's pointing along, it's parallel to these wavefronts, right? And I can see that because it's grad phi here, I want to go parallel to my wavefronts here along equipotential lines, grad phi cross z. So it wants to go along these equipotential profiles. And you say, okay, fine. So how does this affect something in a bulk system? So in a bulk system, it turns out that there is no change in the density profile of the system if I add this enormous velocity in the bulk system. I don't build it up anywhere. So if I don't build it up anywhere, I won't change the electric field distribution potential of my system, and so it doesn't really change the plasma dispersion inside the bulk of the system. The reason is that there's no surface around in the infinite bulk to be able to accumulate these densities due to this extra velocity term that comes in. But something can happen if you go to a boundary, to a surface. So let's consider the system where we have an edge. So what happens here is just now I told you there was these velocities going up here, down here, up here, down here, extra. There's an extra component of velocity from the enormous velocity, and it doesn't really want to accumulate anywhere. But as you can see, if I now go into, say, a system with a boundary, that extra velocity will accumulate charges at the surface. So it's going to impinge charges here, impinge charges here, just going to take it up and down, and I'm going to be able to create some kind of extra density and extra potential along this boundary here. And now we can see, how will this affect plasma dispersion along the system. And now what I'm going to consider is I'm going to consider some kind of plane wave going along this direction at this boundary, along y. Okay? And I'm going to look at this oscillating plane wave of potential. So if I have an oscillating plane wave of potential, as we learned from before, the anomalous velocity contribution goes parallel to the wavefronts or along these equipotential lines. And so if I just stare at this now, I can draw my equipotential lines, these are my equipotential contours, and now I can just put in small little arrows of where my anomalous velocity contribution is pointing. So it turns out that for different potentials, for plus, minus, which correspond to these different densities, I get my anomalous velocity contribution pointing in opposite directions. But they point along my equipotential profiles. And so I can see here, for this system, I'm going to increase my density here as a function of time, decrease it here, increase it here as a function of time. And so if I just track where my positive density is going, it's going this way. It's going to your left, right? So it's going this way. So I'm boosting, because of anomalous velocity, I'm boosting this plane wave mode to the left. And so I'm allowed to now think about two different kinds of plane waves, one propagating to the right, one propagating to the left. And I'm going to say, how does anomalous velocity now alter the velocity or the frequency of these plasmas? Well, if anomalous velocity is pointing to the left, then this wave propagation direction, the anomalous velocity assists the motion. So it's going to make it faster. So its frequency is going to go up, right? And likewise, if I now consider this plane wave here, which is going to the right of my system, it's going right this way, then the anomalous velocity counteracts the motion. It goes against the original phase velocity of the system, and so it brings it down. And so it brings down its velocity, and it also brings down its frequency as well. So as a result, what happens is you get this kind of edge-confined chiral edge barrier plasmon along the edge of the system here, whereby I used to have maybe these dashed lines, used to be my plasma dispersion here, which was not chiral. And now I apply anomalous velocity. I apply very curvature anomalous velocity to my system. I boost the one going to the left, as we showed before. Anomalous velocity boosts the direction going to the left, and then it brings down the one going to the right. Right? And as a result, these edge-confined modes will have something which is non-reciprocal. So the propagation direction going this way and that way have different frequencies and different velocities as well. And this is given by the fact that there is some finite Berry flux, a very curvature system. Okay. So given that, we can say, okay, fine. That was a bare bones kind of explanation for how to get the frequencies for the system and where it comes from physically, intuitively. We can go through a calculation and find it out just using continuity equation and changing how velocity is given by momentum and also phi. So there's an anomalous kind of constitutive relation which relates velocity and momentum and get this extra component. And then I can seek the solutions close to the edge of the system, solving Poisson's equation, using appropriate boundary conditions, and then as you can see here, the amount of charge pile up on the edge gives a jump in the boundary condition for partial x phi. So that's how one can arrive at Berry plasmons. But it's perhaps useful now to maybe talk about what the splitting is. So I'm now talking about a particular edge mode, plasmonic edge mode, confined to the edge of this metal, and they have these split dispersions, omega plus and omega minus, due to Berry curvature. And one can estimate for small q what the splitting is between omega plus and omega minus, the left going mode and the right going mode. And one can find that this scales with q, scales with the interaction factor e squared over kappa, scales with the Berry flux, F appears at zero magnetic field, and A is something which depends on the geometry of the system. And it has the key attributes of this is that it splits at zero magnetic field, it depends on interaction, it's sensitive to the wave vector Q, and if we plug in some numbers for this, we find that the splittings between the omega plus and omega minus can be of order 10 to 100 MeV, depending on the Q wave vector that you choose, right? And you say, okay, fine, no, this is interesting. How does this compare with chirality achieved by Lorentz force, by magnetic field, right? So we recall again that chirality achieved by Lorentz force is governed by the cyclotron frequency, EB rem. And that's what we covered in the first slide. And it can also give you magnetoplasmons. The cyclotron frequency can also give you magnetoplasmons in a metal as well. But first of all, it requires a magnetic field because omega C scales with B. It's like a single particle property as well. And it's splitting, so that the splitting actually lowers omega C as well. The splitting between omega plus and omega minus modes lowers omega C, and it's not very large if you put typical values. So there actually it's quite a big difference between splitting for these Berry plasmons as compared with magnetoplasmons. Magnetoplasmons, a purely single particle property for their splitting, does not depend on Q wave vector, does not depend on interaction parameter, and needs finite magnetic field. And the splittings is order few MeVs for fairly reasonable magnetic fields. And here, without the magnetic field, you get fairly large splittings already. So there's a big difference already, as you can see, between the Berry plasmons and magnetoplasmons. Okay, the confinement between the omega plus and omega minus modes along the edge actually depend on the Berry flux as well. So at a certain point, the omega plus mode, which gets boosted by anomalous velocity, actually merges in with the bulk system, which merges in with the bulk plasma dispersion. As you can see here, the confinement just doesn't want to get confined anymore. It just kind of wants to go into the bulk. and as you can see here, this is what happens with that blue curve. It hits into this omega Q bulk system. Great, so we can ask, great, we can write this down, and we know these omega plus and omega minus modes for these edge Carroll-Berry plasmons. One can ask the question, how will I see this? Experimentally, how will I do it? And one way of looking at plasmons, apart from using very near field techniques, bringing down a tip and shining some light inside of a plasmon, is to actually build some kind of disk and have these kind of finite disks in my system. I shine light on that system and try and see what the absorption spectra of that large array of disks look like. And so we can look at it here, whereby we can look at the whole entire density of the system, and we displace electron density, and I create some pluses, excess plus charge and minus charge on one side. This creates an electric field, and of course this also gives me a new kind of anomalous velocity thing here as well. This density now moves, or this basic position now moves according with this extra anomalous velocity. And so we can solve this, and we find that there are two Carroll modes. So I can think of now my disk plasmon, and my disk plasmon without magnetic field, without Berry flux, will have two modes, and they're at the same frequency with each other. But now I apply some kind of Berry flux into my system, and I basically boost again the counterclockwise mode. This fast mode here becomes faster, and I get an extra frequency from this. And we can calculate again how large the splitting between this fast counterclockwise motion and clockwise motion are. And we find actually that can be fairly large. So this D is the diameter of my disk. And so if my disk is something like 1 micron, I get some kind of splitting of about 9 eV. So that's fairly large. It can be kind of seen in experiments. How I'll see it in experiments, I'll look at the optical absorption of this system, and what happens is, without any Berry flux or magnetic field, I just get this peak due to my plasmons. And then when I apply some kind of Berry flux, it just splits that peak into two peaks, one for omega plus and one for omega minus, and that now can be controlled by the distance, by this diameter of my disk, and my Berry flux as well. Very good. So what materials will I see this in? So I'll say yes, in these anomalous Hall metals. If I take the system and I dope it a little bit up onto this side, so I have some kind of density, I will have some Berry flux as well. And in the system, I expect to see some kind of Berry plasmon in either the disk formation or along the edge. But I can also do this in a slightly different way. I can look at these gap-to-rock materials, like transition of like calcinites or graphene or nitride, that we've heard from before, actually Tuesday, actually Monday, and I can also apply certainly polarized light to excite density just in a single value K or value K prime. There are particular optical selection rules which allow me to do that. In these systems, people have seen, the Q group of Cornell has seen a Hall effect in these systems at B equals to 0, but controlled entirely just by shining circular polarized light onto these systems. So this was on MOS2, and they were able to see a Hall current which was controlled by the helicity of the light that you choose. So since they can see a Hall effect in the system due to Berry curvature type effects, then you can say maybe I can also see these Berry plasmons in these systems as well. And one can calculate this in the disk formation and see that the omega plus, omega minus, the counterclockwise or the clockwise plasmon disk plasmons will have a splitting which depends on the photoexcited carrier density in each of the values K and K prime. And so by doing this, you can control the splitting, and you can control the absorption spectra that I showed you before. You can control this absorption spectra because you're changing the Berry flux as well. So with that, let me just leave you with a couple of things. So first of all, Berry curvature interactions can give rise to interesting behavior, and when combined with these interactions in, say, metallic type systems, you get these kind of edge confined modes, even without any kind of quantum mechanical edge states arising from topology, it just comes from Maxwell's equations. So just a consistent, so Maxwell could have solved this if he wanted to, if he knew about Berry curvature, and he would have found these Chiaro-Berry plasmas as well. The slings are fairly large. They're controlled by interaction parameter by a wave vector and by Berry flux. And it can also maybe kind of offer a new way of achieving these non-reciprocal propagation in these systems. But before I finish, so I was talking to some of the organizers, a couple of days ago they said maybe it might be useful to introduce a bit what Singapore is and what research opportunities, especially for undergraduate people who are thinking about PhD programs. So I'd like to maybe spend maybe 2-3 minutes telling you what Singapore is and what programs are available. So hopefully there are some undergrads or people interested in programs in Singapore. I'll just tell you a little bit. Singapore is tropical, and it's a fairly high. This is actually 4 a.m. in the morning, so it's 28 degrees 4 a.m. in the morning. So that's fairly high. It's today. Sorry.
It's 28 today.
Yeah, that's right. It's 28 at 4 a.m. on Thursday, their time. Yeah, that's right. So this is in the morning. All right, so it gets considerably high. Oh, we get lots of questions about this. Fantastic.
That's not advertised.
That's not well. Okay, fine. Well, it's better than here, I would say, than the weather. But if you like the cold, then you might. I don't know. So, sorry. But it's the tip of the Malaysian peninsula. Malayan peninsula down here. It's really small. The scale bar here is 5 kilometers, and that's 5 kilometers here. So it's really small. That's just all there is. It's a pretty cosmopolitan place. You have the city. You have lots of housing places. Nice blue sky. This is the university map with about 10,000 grad students, about 20,000 undergrads. Also there's a PhD program as well for people interested in physics. There's no need for a master's degree to apply for this program. You can apply directly from your bachelor's. It takes approximately 4 years. It's fully funded by scholarships. There are numerous programs, and our division has about 40 faculty, lots of research. In addition, on top of that, if you want to find out a bit more about the PhD program before actually going into it, there's an internship program that you can apply for as well, which is paid for. They give you an allowance, approximately about 3 months. You can go there over the summer or some other pre-arranged time, and you can get into this internship program for the PhD before you commit to a PhD program. It's all available, and it's all available on the website, so just have a look at it. So we're looking for people, just let me know, and feel free to contact me about Singapore, about life there as well. So with that, thank you for your attention. I'll leave you off with this. Thank you very much.
Questions? Yeah.
Yes.
Maybe general question about very basic calculations.
Yes.
Usually people they're presenting some results based on Berry phase, but nobody talks about how do they calculate the Berry phase. I mean the number. So, for example, just to estimate how strong is effect. So, and there is one way how to calculate using crystalline structure, band Bloch waves, and so on, so on, so on. You have a formula for it, but it's one particle picture. And so, my first question: how do people do it in general? So, in your business. And second one, if you are considering effects of interaction. So does the Berry phase, or so this number change with if you include interaction? Because one particle picture doesn't work in the case of interaction.
Thanks very much for that question. It's wonderful. So let me just answer your question in parts. So on the first part, how do people calculate it? So people just put it into the computer and they calculate it. That's one way of doing it. But a lot of people who work on this also work with analytical models, right? And so their favorite model of choice is Dirac model. So I write down, V sigma dot p, and I can diagonalize this by hand. right? And I can just put it in and I get a number. I actually do get a number for the momentum that I choose and for the velocity that I choose and for the gap size that I put in as well. With that, you can actually calculate actual magnitudes for the single particle. So if I choose a Dirac model. And the wonderful thing about the Dirac model is that these systems are, these gap-to-gap systems are quite good approximations of them. So I use the Dirac model, just put it in, and it's pretty, describes the TMDs quite well, describes graphene quite well. So that's that. And on top of that, this describes these Dirac semi-metals quite well as well. And so there are a variety of systems where these low-energy Hamiltonians work pretty well. And so, yeah. So recently there have been some experimental kind of comparisons as well. And so there's ability to compare how good these low-energy Hamiltonians just calculate single particle phenomena are. The second part of the question, very good question. It's very interesting. It could possibly kind of affect it, and people have written down formulas for how to treat it in interacting systems. However, if you consider weak interactions, and that's what we've considered here, the hope is, you can say, I'm only perturbing the system only very little bit with interactions. I'm only looking at these plasmons, which are not, they don't kill your system entirely. They don't actually give you a new phase. So weak interactions, then you can say, fine, maybe the way to think about it is, how does this kind of change this kind of velocity here, this definition of velocity density of the system? And by thinking about that, one can possibly maybe understand weak interactions, how barrier curvature and weak interactions kind of interplay in these systems. Hopefully that helps. Yes?
So when you have barrier curvature, in general you have orbital magnetic moment for quasi-particles, right? So if you consider some mode for which density changes, you actually have density of those moments that changes and magnetization, hence the related current, curl magnetization kind of current.
Yes.
So is it somehow obvious that it's small compared to the currents that you took into account when taking into account anomalous velocity, or yeah? Are these currents small compared to the currents that you took into account?
I don't know. We need to think about that.
There's a question here.
As I understand, the difference in omegas, they're controlled by Berry flux. And this Berry flux is controlled by field if you are in the material that meet a magnetic field. And how do we estimate the Berry flux in the material where there is no magnetic field needed to create a Berry phase?
Okay, so that's, thanks very much for the question. Maybe there was a little bit of confusion, maybe just to make it clear. For most of this place, I've considered magnetic field that is applied is zero. Zero applied magnetic field. So maybe you're thinking about these, chromium doped topological insulators. You might think, okay, there's it's magnetic material, and so maybe that's what you're thinking about. You could estimate that basically from bench calculations or also from these low energy models. But in these other materials where I just talked about transition metals, dicalcinites irradiated with certainly polarized light, for example, here one can actually explicitly calculate the Berry flux in these materials. Why? Because I have just low energy Hamiltonian material, low energy Hamiltonian here, and I know selection rules and Fermi's golden rule kind of calculation to try to get the amount of carriers in this thing. So as a function of irradiated circular polarized light, one can actually calculate it just by putting photoexcited density into my system here. And the reason why I do this is because I'm using some low energy Hamiltonian, which describes these gap-to-rock materials, which is transition metal dicalcinides, graphene and boron nitride, and dual gate bilayer.
And how big is it? Because there was a formula involving the barrier flux, and to understand how.
Yes. Yeah.
What is energy gap? We need to input a number.
Yes, that's a very good question, and that's wonderful. So if you're concerned about these materials which are transition metal dicalcinides, so gap-to-rock materials, it turns out that if I go to very small gap sizes, for example, 20 to 30 MeV gap size in graphene boron nitride, and I irradiate it with certain polarized light, F can be as close to 1, can count to 1. So this F number I can get actually multiples of 1, depending on degeneracy as well. So I'll get something close to 1, and I don't actually need that much photoexcited density here. So I actually show you a calculation here, right? This is just the photoexcited carrier density inside each of this K or K prime, right? And as you can see, this gap is quite large. As compared to
There's one question.
Just to clarify, so your motivation effectively, you showed like quantum Hall effects and some quantum effects were motivation for your work in the sense. In the end, also you ended up with quantum effects. However, you were using effectively a simple drift diffusion type of model, even without generalization to quantum, sort of quantum drift diffusion type of models. And you don't have like, in your carrier density, right, you don't have any nonlinear effect or combination generation as expected. Could you please clarify why such simple model may work in this situation?
Oh, great. Thank you very much for the question. So I think there are a couple of parts to that question. So let's do this.
Can you use the mic? You'll need a quick answer now.
Oh, quick answer. I'm sorry. Okay, so let me just say that the Berry curvature is quite mechanical. So calculating the Berry curvature, I've pushed everything into the flux here. I said that effectively the kind of hydrodynamic model of how the density moves around goes according to this thing, and I've included my quantum effects.
It's a big assumption.
No. Let's sit down and talk about it if you like. So don't be afraid. But then we can talk about the other side.
Good. Thank you.